So this week we're going to be using the lab technique of titration. It's a stoichiometric technique to determine the amount of acid in a drink. So there are two ways to do this, either with indicators or with a pH curve, and I'll walk through both of those here. A titration is a common laboratory method used to quantitatively determine the concentration of an unknown solution. I should emphasize that you know what you're looking for, you just don't know how much of it is there. We're going to use a titrant. The titrant is a solution of known concentration, and we're going to add that to our analyte solution, which is the solution of unknown concentration, until it reaches its equivalence point. So the titrant is going to react with the analyte in a known way, of a known stoichiometry, until you get to the equivalence point, which is the point at which enough titrant has been added to react with all of the analyte without having any leftover reagents. So you're going to use up all of your reactants. This is a technique that's not limited to acid-base reactions, and in fact the next lab that we do will be EDTA titrations, where we do a complexometric reaction, but here we're just talking about acid-base reactions. So here's our first example, simplest example of a strong acid that we're going to react with a strong base to form water and salt. So how this gets set up with an indicator is that in the Erlenmeyer flask at the beginning of the titration, this is where we have our acid solution, or our analyte is typically in the bottom, and then we have our titrant in the burette. So we have hydroxide up here is our NaOH, that's our titrant, and we have an unknown concentration of acid in the flask. So at the beginning of the titration, we start adding sodium hydroxide, and here we just have the hydroxides and the hydrogen ions present. As this reaction goes, we drop hydroxide into the flask, and the hydroxide ions will react with the hydronium, or with the hydrogen ions, the protons, to create water. And we just keep adding more hydroxide until all of these protons have reacted with hydroxide to make water. At the equivalence point then, we have exactly used up all of the acid ions, and we don't have any extra hydroxides. Okay, so at the equivalence point, we have no sodium hydroxide left over, we have no HCl left in solution, we only have liquid water and sodium chloride present. So we start with an acidic solution in the flask, pH that's less than 7. We have a known volume, so maybe that's exactly 25 milliliters. We need to know that, but we have an unknown concentration of acid. As we add the base, the pH is going to rise as we use up that hydronium ions, or those protons, until we get to the equivalence point. If we neutralize the HCl exactly without excess, then we'll have a pH of 7 in our flask, and we can measure the volume of titrant that was required to get to that point. And we know the concentration of the titrant, so we can use those two things to find the moles and then do our stoichiometry problem like in the previous video. So here we're relying on an indicator to change color when we get to that equivalence point. And once we do, we stop to make sure we're not adding any extra NaOH, and then we measure this difference in the burette as the volume of titrant added. Okay, so we can use the known concentration and volume of NaOH to determine the moles of NaOH. We can use the mole-to-mole ratio from the balanced chemical equation to convert moles of NaOH into moles of HCl, and then use the moles of HCl and the initial volume, which I said before was 25 milliliters, to determine the analyte concentration. So this problem looks a lot like what we did in the previous video. Here is the volume of titrant and concentration of titrant that were used to get to the equivalence point. So I'm going to start there. Concentration and volume is going to give me moles of sodium hydroxide, and then I can use my mole-to-mole ratio for my balanced chemical equation to get to moles of HCl, and then I can use the moles of HCl and the volume of HCl to find the concentration of HCl. Now, if you have done acid-base titrations in the past, you probably used phenolphthalein as an indicator. It is bright pink. So while you are in an acidic solution and you still have hydrogen ions present in solution in excess, it'll be clear. And when you get close to the equivalence point, it'll start to turn this very faint pink color, and you'll mix it until that faint pink color becomes permanent. And then if you go even one drop over, it'll just be fuchsia. So it really identifies that equivalency point very precisely. Now, what's the problem with using an indicator for an acid-base titration? If we're going to look at how much acid is in a drink, for example, in Gatorade, that's blue or green, or Minute Maid lemonade, we can't use an indicator because these drinks are already very colorful. And so we are not going to be able to see a color change in these drinks if we're trying to measure how much citric acid is in a drink. So we need to look at the pH curve. Now, I mentioned that the pH is changing as you're doing this titration. So let's look at a simulation of this titration and see if we can identify where that endpoint. So there's a simulation video on YouTube, and I'll post a link to this in the PowerPoint notes. But you can see here we have some amount of HCl present, and then here's a particulate view of that solution, right? So here's my protons, my hydrogen ions, and here's my chloride ions, and they're all separated from each other in solution. And we're going to start to titrate this. My pH is very low right now, okay? We're going to start the titration, and they're going to hit this button up here that says Begin Titration, and add 5 milliliters of NaOH. So we're starting here at pH 1, and then when I add 5 milliliters of NaOH, you can see that here's my sodium, right? Here's my hydroxide, pairs up with hydronium ions to make water, okay? And we're slowly reacting away all of those loose protons, okay? Now, as we do that, we're decreasing that hydronium ion concentration, and therefore we're increasing the pH. And at some point, we're going to use up all of these H+ ions, right? All these hydronium ions. And when we do that, we are going to be neutral. Now, in a titration with an indicator, this is where we want to stop, right? We want to stop at this point where we have exactly used up every hydrogen ion with a hydroxide, and now all we have is salt and sodium and chloride, okay? In a pH curve titration, we're going to continue this measurement, and we're going to go beyond that equivalency point and add extra NaOH, and now our pH is going to rocket up to very high pHs because we're adding excess NaOH, okay? So we're going to look at this curve in its entirety to try to figure out what is the equivalency volume. Now, one way that you can do that is just to look at the steepest part of this rise and say, okay, right here in the middle of this rise, where I know my equivalency point should be at pH 7, I'm going to go across to my equivalency point, and I'm going to come down and say, oh, that's about 30 milliliters. But there are a few other ways to look at this as well to help you be more accurate. So here's that pH curve. We've gone past the equivalency point. Again, we can find the steepest part of that rise, the middle of the rise, and then come straight down and look at the volume that we used. This can be very hard to pick out. And so if we apply a little mathematical manipulation, we can take the first derivative of this curve, and we'll see at that inflection point, because we have a concave to a convex, at that inflection point we will see a spike in the first derivative curve. So here the peak of the first derivative curve should show you what the equivalency volume is in that titration. Now, experimentally, sometimes this is pretty messy, and so we get a more reliable number if we look at the second derivative. So the second derivative is going to show you where that equivalency volume is, but in a crossing of 0. Okay, so again, this is concave to convex, and so we get a crossing of 0 when this goes to a maximum. So right here we get a maximum value in the first derivative. That's going to be a crossing of 0 in the second derivative. And this point is a lot easier to pick out in actual experimental data than the first derivative. So we're going to have you looking at this curve and also the first derivative and also the second derivative. This week we'll be looking at citric acid in your drinks that you looked at last week. We will not be using Hawaiian Punch because that also has vitamin C, which is ascorbic acid, and that can then you're detecting total acid concentration, so we're not going to look at that. So we're just going to use the other 3 drinks and look for citric acid. Here's the molecule for citric acid. 2 things about this. It's a polyprotic acid, so we see that there's 3 acidic protons for every 1 molecule, which means our stoichiometry is 3 to 1. But it's also a weak acid. And so at the equivalence point, the solution will be slightly basic. Now to show you what this might look like, the 3 protons that come off are actually these ones that are attached to what we call carboxylic acid groups. So here we have a double bonded oxygen adjacent to an OH, and those are the ones that are going to come off. We'll talk about that in second semester general chemistry. But how this affects the curve, the titration, the pH curve, for example, this is sulfuric acid. Okay, sulfuric acid is a polyprotic acid. You can think about removing these acidic protons in 2 steps. So first we remove an acidic proton from 1 proton from every molecule first, and then we remove the second proton from every molecule. So step 1, right, we remove only 1 of these acidic protons, and now we have an acidic salt. And that shows up here, right, and here's the first step. And we have the 1 equivalency point, and then in step 2, we remove the second proton, second acidic proton from that acidic salt and react that to create water, and now we have just a salt left over. And that's the second equivalency point. Now the tricky thing about polyprotic titration curves is that you may or may not see both of these or all of the equivalency points depending on how easy it is to remove each one of those protons. So for this curve in particular, this is for sulfuric acid. It's actually super easy to remove the first proton, but it's actually pretty hard to remove the second one. When we're looking at citric acid, we will not see all 3 ionization events. Instead, we're only going to see the culmination or the last one. The other factor here is that citric acid is a weak acid. And so what that means is when we are done titrating and we get past our equivalency point or to our equivalency point, when we are at our equivalency point, we have used all of our citric acid. We have no more NaOH left over. What we have left over is sodium citrate. Okay, and that citrate will act as a weak base in solution. And so according to our Arrhenius definition, if you dissolve this into water and it produces hydroxide, it can act as a base. And so this does act as a base, and what that means is at the equivalency point, you have a pH that is higher than 7 or greater than neutral. A strong acid, strong base would have an equivalency point at exactly 7. A weak acid will produce as a product a weak base, and so your equivalency point will be greater than 7. So when we do our pH curves, you will probably not see multiple equivalency points. You'll just see the last one, okay? So you can do your 3 to 1 stoichiometry problem. And then we're going to also have you identify that point here as in the main curve, the pH curve, also in the first derivative, and also in the second derivative. So you should get the same number here. This is going to be the most reliable. And then you can use that equivalency volume to do your stoichiometry problem. So here's a problem that you can try on your own. Pause this video. Again, we're using the information we know about sodium hydroxide to find the moles of sodium hydroxide. We're using that mole to mole ratio to find the moles of citric acid. And then we're going to divide by the volume of your drink that you had to get the molarity of citric acid.